Hello there, and welcome to the Celestographer channel. Tonight we are looking at one of the strangest possibilities hidden inside modern physics. What if somewhere beyond everything we can see, another person is living with your face, your memories, and the same certainty that they are the original? What if that person never appears because the distance between you is greater than any signal could cross? Or what if the separation is not across space at all, but inside the way reality itself unfolds? These ideas sound like science fiction, yet some of them emerge from serious attempts to understand the universe. They also lead to a much harder question. Would a perfect copy truly be you, or only someone who believes they are? And if other outcomes exist somewhere beyond your reach, do the choices made here still matter? Tonight, we will follow the physics as far as the evidence allows, without pretending that possibility is proof. We will look at where observation ends, where interpretation begins, and why the line between them matters. Before we begin, subscribe to the Celestographer on YouTube for more calm, long-form documentaries about space, physics, and the mysteries hidden beyond the visible universe. For now, look toward the dark window. There is only one reflection. The question is whether that means there is only one of you. At night, a dark window can act like a mirror, returning one face from one room and making the view feel complete. The reflection moves when you move, pauses when you pause, and seems to confirm something so ordinary that it is rarely examined. There is one body standing here, one remembered past behind it, and one chain of choices leading into this exact moment. We wake in one place, speak through one voice, and carry memories that seem to belong to a single continuous self. Nothing in ordinary experience presents a second Earth with the same oceans or a matching person remembering the same childhood. That absence feels persuasive because the human mind trusts what remains nearby and visible. Yet it does not prove that existence contains only one instance of every possible arrangement. Our knowledge of the cosmos comes through a narrow opening, more like looking through a keyhole than standing inside the whole building. We have observed a small region for a brief span of time, then treated that local sample as a statement about everything. It is like opening one page in an enormous library and assuming no other volume contains the same sentence. Several different scientific proposals are often gathered under one dramatic word. The word multiverse does not describe a single theory with one level of evidence. It can refer to distant regions of ordinary space, separate cosmic domains produced by inflation, or quantum histories that no longer interact. Those ideas do not begin from the same assumptions, and they do not carry the same scientific weight. A distant physical counterpart would be another arrangement of matter somewhere beyond any reachable horizon. A near copy might share almost the same history while differing in one event, one conversation, or one biological detail. A quantum branch would begin from a shared physical past before later outcomes became effectively separated. None of these possibilities involves a spiritual double, reincarnation, or a symbolic alternate life imagined after a missed decision. The question is physical. Could matter, space, and the laws describing them produce more than one matching instance of a person? For the moment, the room remains unchanged. The walls have not moved. The glass still holds the same faint reflection, and the air carries no sign of another history. Outside, the night appears empty because distance hides detail long before darkness becomes meaningful. The silence does not tell us what lies beyond the reach of our instruments. It only tells us that nothing beyond that reach can answer from here. The room is not proof of cosmic singularity, only evidence of one local point of view. One observed life is not evidence of one possible life. That does not establish another counterpart. It only removes an assumption that was never measured. Science becomes useful here because it separates what feels obvious from what can actually be demonstrated. Human instincts were shaped to recognize faces, predict nearby events, and survive within a small part of one world. They were not shaped to judge the full size of space or the arrangements that physical law may permit. That is why intuition can be reliable across a room and misleading across the cosmos. From dependable daily experiences, the mind builds a larger picture in which all existence must also be singular, continuous, and closed. The problem is that this picture reaches far beyond the evidence used to draw it. Modern cosmology does not begin by declaring that copies exist. It asks how far space extends, whether matter can repeat local arrangements, and whether observed laws continue beyond the region we can see. Quantum theory raises a separate question about whether different outcomes can remain within one physical description even when each observer experiences only one. These claims are not interchangeable, and blending them creates confusion before the investigation has started. A careful argument must keep observation, inference, interpretation, and speculation apart. Observation tells us what instruments have measured, while inference extends those measurements through established laws. Interpretation asks what the equations describe as physically real, and speculation begins where assumptions become difficult or impossible to test. The possibility of another you can appear at several points along that ladder, but it does not stand at the same height in every case. The responsible starting point is not to ask where such a person might be hiding. It is to ask what the universe would have to be like for another you to exist at all. A beam of light entering a telescope is never a picture of the present. It is a message carried across distance, and every mile it travels also carries it farther into the past. Look at the moon, and you see it as it was a little more than a second ago. Look at the sun, and you receive light that left several minutes earlier. Look toward the most distant galaxies, and the delay becomes billions of years. This means every telescope is also a time machine, though only in one direction. It collects old information that has finally reached us. The observable universe is the largest region from which light has had enough time to arrive under the history of cosmic expansion. That region spans roughly 93 billion light-years from one side to the other. The number can sound contradictory because the universe is nearly 14 billion years old. Light has not been traveling through a fixed and motionless arena during all that time. While the signal crossed space, the distance between widely separated regions continued to grow. Imagine two marks drawn on a surface that is slowly being stretched. A signal moves from one mark toward the other, yet the separation keeps increasing while the signal is already on its way. The comparison is limited, but it captures why the oldest visible regions are now much farther away than their light travel time alone would suggest. What we call the cosmic horizon is therefore not a wall. It is the current shoreline of information, the farthest limit from which any signal has been able to reach this location. No spacecraft could arrive there and touch a final surface. No sign would announce that space ends beyond it. If an observer somehow occupied that distant region, the surrounding cosmos would appear ordinary from their point of view, and they would possess a horizon centered on themselves. Stand for a moment at that imagined boundary. There is no fence, no cliff, and no final line painted across the darkness. Galaxies would continue in some directions, while others would fade beyond the reach of sight. The observer would not feel suspended at the border of creation. Only the flow of information would reveal that certain regions could no longer communicate. The limit belongs to causality, not to the material of space itself. This distinction matters because the visible cosmos may be only part of a much larger whole. Space could continue far beyond everything our instruments can detect. It could also possess a finite size while wrapping around through a global shape that ordinary experience does not prepare us to picture. At present, neither the total size nor the overall connected form of the universe is known. One of the strongest clues comes from the cosmic microwave background, ancient radiation released when the early cosmos became transparent enough for light to travel freely. Researchers study tiny variations in that radiation to test the large-scale geometry of space. One method examines how enormous triangles would behave across cosmic distances. On a curved surface, the angles of a triangle do not add together exactly as they do on a flat sheet. A triangle drawn across a sphere, for example, can contain more angular space than one drawn on a table. Measurements of the ancient background light are consistent with spatial flatness within current observational limits. That result means the geometry we can test behaves very closely to ordinary flat space on the largest accessible scales. It does not, however, establish that the universe continues without limit. A flat space can still be finite if its overall topology connects distant directions back onto one another. Topology is the universe's large-scale connected shape, not merely whether a local patch bends. A room in such a cosmos might have no boundary even though its total volume remained limited, much as a traveler could continue forward and eventually return without encountering a wall. The exact comparison should not be taken literally, because the possible cosmic shapes involve more dimensions and more complicated connections than an ordinary room. It simply shows why flatness and infinity are separate questions. The evidence gives a precise description of what lies within reach, while leaving the larger form unresolved. That uncertainty is not a failure of observation. It follows from the fact that information travels at a limited speed through an expanding cosmos. Beyond some distance, light has not had enough time to arrive. Beyond another, continuing expansion may prevent any future signal from reaching us at all. The unseen region is therefore hidden by more than faintness or darkness. It is separated from us by the structure of space, time, and cause itself. Consider a simple box containing a limited set of pieces. Those pieces can be arranged in many ways, yet the number of distinct arrangements remains finite if the box and its contents are finite. Fill enough identical boxes, and eventually one arrangement must appear again. The logic is simple at this scale because the pieces, the boundaries, and the rules are clearly defined. A region of the universe is far more difficult. It is not literally a box. Matter is not a collection of rigid puzzle pieces, and quantum fields do not behave like objects laid across a table. Even so, several modern frameworks suggest that a bounded volume with finite energy may possess only a finite, or effectively finite number of distinguishable physical states. That number could be so enormous that ordinary language offers no useful sense of its size. The important point is whether the count has a limit. If a finite cosmic area can exist in only a limited number of physical arrangements, repetition becomes possible once enough areas are considered. This is where the argument becomes conditional. Space would need to extend without a known limit. Matter would need to continue appearing with broadly similar statistical properties. The same physical laws would need to remain valid beyond the part of the cosmos we can observe. The allowed local states would need to recur rather than drifting into different conditions forever. Only when these assumptions are placed together does repetition begin to carry weight. Infinity is not the whole argument. One reason physicists take the idea seriously is the cosmological principle. On the largest visible scales, the universe appears approximately uniform from place to place and approximately the same in every direction. Galaxies gather into clusters and filaments, so the cosmos is clearly not smooth at every scale. Yet when researchers average over sufficiently large distances, the broad distribution of matter becomes remarkably consistent. No observed direction appears to occupy a privileged position. This regularity supports the idea that space beyond our horizon may resemble what we can already see. That extension remains an extrapolation. We cannot observe the entire cosmos and confirm that the pattern continues forever. We can only note that every accessible direction has so far followed the same broad physical order. It is like finding page after page printed with the same alphabet and grammar, then asking whether unseen volumes obey the same rules. The evidence gives a reason to expect continuity, but it cannot guarantee what lies beyond the shelves we can reach. If that continuation holds, and if local states are limited, then sufficiently distant domains could repeat arrangements already found here. A recurrence might reproduce a planet with the same oceans, atmosphere, and evolutionary history. An even more exact recurrence could reproduce the same room, the same objects, and the same brain state at one chosen moment. Near copies would require less precision. A distant Earth might match this one until a storm formed differently, a mutation occurred in another cell, or a conversation ended with another sentence. Those small deviations could later produce histories that no longer resembled each other. Perfect recurrence is more restrictive because every relevant detail must align. Under the required assumptions, however, an unbounded number of opportunities would not produce one matching domain and then stop. The arrangement would recur repeatedly, separated by distances too large to express usefully. Now let the argument settle into an ordinary image. Somewhere beyond every visible galaxy, suppose there is another night sky arranged exactly like this one. Beneath it sits another planet with the same clouds, coastlines, and lights scattered across sleeping cities. In one building, a room remains quiet. A person stands near a window, hearing the same words and carrying the same remembered history. Nothing there would reveal that the arrangement had occurred elsewhere. Each local world would feel complete because neither could receive information from the other. This conclusion is not a measurement, a discovery, or a known address. It is what some cosmological models imply. If unbounded space, finite local information, recurring matter, and stable physical law all hold together, remove any one of those premises, and the conclusion may fail. Space could be finite. Local states might not be limited in the necessary way. Matter beyond the horizon could follow a distribution that never reproduces this arrangement. A future theory of quantum gravity could alter the state counting argument entirely. The logic therefore deserves neither dismissal nor certainty. It shows that another matching region does not require a hidden dimension, a separate quantum branch, or a new act of creation. It requires only more ordinary space than any observer could ever survey. In another room, impossibly far away, someone hears these same words. The chair beneath them has the same scratches. The glass beside them contains the same amount of water, and the clock shows the same moment. Their body carries the same scars. Their brain holds the same memories, and their attention moves through the same sequence of thoughts. From inside that room, nothing feels copied. Every remembered conversation appears original because every memory supporting that belief exists in the matching brain. The person does not feel like a second version. They feel like the only one. A perfect physical duplicate would require more than a similar face or a shared personality. It would require the same bodily structure, the same neural connections, the same chemical conditions, and the same immediate expectations at the chosen moment. The arrangement would include details too small for ordinary awareness, from the activity of individual cells to the precise state of signals moving through the nervous system. If consciousness depends entirely on physical organization, then both people would report the same private history. Each would remember the same childhood rooms, the same losses, the same mistakes, and the same quiet moments no one else had witnessed. Both would expect the next sentence to continue in exactly the same way. That agreement would last only while their surroundings remained identical. A single photon entering one room from another direction could begin a difference. One person might blink a fraction earlier. One clock could drift slightly. A distant sound could reach only one pair of ears. From that instant onward, the two histories would no longer match perfectly. The difference might begin almost invisibly, yet physical consequences would accumulate. A changed glance could alter a thought, which could change a sentence, which could reshape the rest of the day. Near copies are therefore less demanding than exact counterparts. They may share nearly every large feature while differing in one local event or one biological detail. Because fewer conditions must align, recurrence models would place such similar regions closer than perfect replicas, though still far beyond any practical reach. Physicist Max Tegmark has used illustrative calculations to show how extraordinary those distances could become under particular assumptions. These estimates do not identify an actual location. They are not measurements of where another Earth sits. They show how rapidly the required distance grows when more details must be matched. The exact values depend on how physical states are counted, how matter is distributed, and what cosmological model is assumed. Using giant strings of digits would add very little understanding. The important fact is simpler. Even the nearest proposed counterpart would lie beyond every route available under known physics. Cosmic expansion would widen the separation, and no signal could cross the required distance in time to connect the two lives. No spacecraft could carry one person to the other. No telescope could resolve the matching room. No message could confirm that the duplicate existed. The two clocks would continue from the same starting state, yet they would tick inside sealed domains with no shared channel between them. Now let both rooms become still. In each one, the same light rests against the same wall. The same faint hum moves through the air. Each person waits without knowing that anyone else is waiting. Neither receives a signal, a disturbance, or a hint of recognition. The silence in one room cannot enter the other. The distance does not merely separate bodies. It prevents either life from becoming evidence for the other. Identical does not mean connected. This matters because physical duplication can sound more personal than it really is. A counterpart would not share a stream of consciousness with you. They would not feel your pain while standing elsewhere, and you would not gain access to their thoughts. There would be no hidden conversation between matching minds. Each brain would generate its own experience from its own physical position. The two lives might begin with the same internal description, yet they would remain separate points of view. From outside, an ideal observer could compare the structures and call them exact matches. From inside, each person would occupy only one set of eyes. Unreachable does not mean non-existent, but it also does not make the idea practically available. The duplicate could not become a companion, a witness, or a second chance. Their memories would not preserve yours if your brain changed. Their choices would not repair consequences unfolding here. Their continued existence would not create a reserve consciousness waiting somewhere beyond the visible cosmos. The recurrence argument concerns repeated physical arrangements, not a shared self spread across distance. That distinction protects the science from a tempting emotional shortcut. A matching person may possess the same remembered history without participating in the same ongoing experience. Two identical books printed in separate rooms contain the same words, but opening one does not turn the pages of the other. In the same way, two matching brains could begin from the same physical description while remaining causally independent. Once their environments differ, even slightly, the printed histories begin to receive different endings. The philosophical question of whether they were ever the same person remains open. The physical question is narrower. Under the recurrence model, they would be two matching instances of matter, each complete, each convinced of its originality, and each unable to prove the other existed. Like reflections placed on opposite sides of an opaque wall, they could match in every visible detail and still never face one another. Nearly 14 billion years ago, the early universe appears to have passed through a period of expansion unlike anything occurring around us today. The change did not resemble matter racing outward through empty space. Space itself expanded, increasing distances so rapidly that ordinary motion provides only a weak comparison. The proposed process is known as inflation. It was developed to explain several features that otherwise seemed difficult to reconcile with the early history of the cosmos. One of those features is uniformity. Regions now separated by enormous distances contain ancient radiation with almost the same temperature. Without an earlier connection, it is difficult to explain how those regions became so closely matched. Inflation allows a once small domain to expand until parts of it lie far beyond one another's later reach. A shared beginning can therefore appear across a much larger cosmos. The process also helps explain why space looks so close to flat on observable scales. A tiny curved patch, expanded far enough, can appear almost level to observers confined within it. The comparison resembles standing on Earth and seeing the ground as flat because the planet's curvature becomes obvious only across a much greater distance. Inflation also provides a way for microscopic quantum variations to grow into the slight density differences that later guided the formation of galaxies. Those tiny irregularities became the seeds of cosmic structure. Regions with slightly more matter drew in additional material, while less dense areas gradually emptied. The vast arrangement of clusters and voids visible today may therefore carry an imprint from an extremely early phase. These successes make inflation a leading explanation for the large-scale properties of the universe. They do not reveal the exact mechanism that produced it. Researchers have proposed several models, yet no specific inflation-driving field has been directly identified. The evidence supports inflation-like behavior more strongly than it supports any single detailed account. That distinction becomes crucial when the theory is extended beyond our observable region. In many models, inflation does not end everywhere at once. Quantum fluctuations can cause expansion to stop in one area while continuing in another. The region where inflation ends begins a hot cosmic history like the one that eventually produced our stars and galaxies. Elsewhere, expansion may continue, carrying other regions apart, before the same process ends within them. When this continuation has no final global ending, physicists call it eternal inflation. The name does not mean that every individual universe lasts forever. It refers to the larger process continuing somewhere even while it finishes in particular locations. A loose visual comparison is frost forming across a cold window. Separate patches appear within a larger changing surface, each developing its own boundaries and internal pattern. The comparison fails if it suggests that cosmic regions float inside ordinary space like objects in a room. Under inflationary models, the larger expanding structure is space itself, not a container surrounding smaller universes. Imagine one isolated region after inflation has ended there. It becomes hot, dense, and filled with particles. Over time, expansion slows into a more familiar cosmic rhythm. Matter gathers, stars ignite, and galaxies begin to form. No observer inside that region can see the greater process that may still be continuing elsewhere. The surrounding histories remain hidden not because telescopes are too weak, but because expansion has placed them beyond causal contact. Each region can therefore experience what appears to be its own complete beginning. These causally separated domains are sometimes called pocket regions. They may share the same underlying physics, yet some models allow their effective physical properties to differ. Particle behavior, force, strengths, or other conditions might settle into different forms as inflation ends. If so, many regions would not resemble ours. Some could fail to produce stable atoms. Others might never form long-lived stars or complex chemistry. A large collection of cosmic domains does not automatically create another human life. Abundance alone is not enough. The necessary physical conditions must also repeat with extraordinary precision. This makes inflation a different route to multiplicity than the recurrence argument based on ordinary space. Recurrence asks whether enough similar space eventually reproduces a local arrangement. Eternal inflation proposes a larger process capable of generating many separate cosmic histories. Some of those histories might resemble ours, while others could be radically different. The existence of these pocket regions has not been directly observed. Their scientific status depends on whether eternal behavior follows from the correct model of inflation and whether any observable consequences can distinguish that model from alternatives. Inflation may remain the best explanation for several measured features, even if its eternal extension proves unnecessary or wrong. That possibility is important because scientific frameworks often contain a well-supported core surrounded by consequences that depend on additional assumptions. The core can survive even when the wider picture changes. Early rapid expansion may explain the smoothness, near flatness, and structure of our observable universe without requiring an endless collection of separate domains. Eternal inflation adds scale and variety, but it does not provide a simple or confirmed answer to the question of another you. A microscopic particle approaches a measuring device while its quantum description still contains more than one possible result. The mathematics does not choose a single outcome in advance. Instead, it assigns relative probabilities to the alternatives that the experiment may record. When the device responds, the observer sees one definite result, even though the equations have evolved smoothly from the beginning. That tension lies at the heart of the measurement problem. Quantum mechanics describes possibilities together, while ordinary experience presents one event at a time. The Born rule tells physicists how strongly each result should count when predicting what an experiment is likely to show. It does not explain by itself why one outcome becomes the only one an observer experiences. Some interpretations introduce collapse, a special change in which the quantum description reduces to one measured result. During the middle of the 20th century, Hugh Everett proposed a different answer. He removed fundamental collapse and treated the full wave function as something that always continues to evolve. Under this view, alternatives do not disappear when a measurement occurs. They remain within a larger, physical description whose later histories no longer stay available to one another. This proposal became known as the many worlds interpretation. The name can suggest universes suddenly appearing whenever someone makes a choice, but that image is misleading. The process begins with physical interaction, not with human intention. A photon striking a detector, an atom colliding with its surroundings, or heat entering the air can spread information about an outcome. As that information enters the environment, the alternatives become entangled with different states of the device, the room, and eventually the observer. The process that makes those alternatives effectively unable to interfere is called decoherence. Decoherence does not require a conscious mind. It happens because quantum information disperses into surrounding matter with extraordinary speed. A limited comparison is ink spreading through water. The concentrated ink soon disperses through countless currents, making any exact reversal practically impossible. Quantum information behaves differently, but the comparison shows how a local difference can become recorded across a much larger environment. Once that record has spread, each alternative behaves like a separate classical history for the observers inside it. Consider a device measuring a particle with two allowed results. Before the interaction, the quantum description includes both possibilities. Afterward, one observer reads one result, while another branch contains a matching observer reading the other. Neither person feels a break in time or watches the room divide. Each remembers preparing the same experiment and then seeing one continuous outcome. One notebook contains one result, while another record exists within a history that can no longer send information back. No branch hears the others leave. A quantum counterpart differs from a distant cosmic duplicate because it shares an earlier physical history before decoherence separates later records. Branching also does not wait for a dramatic personal decision. Light scatters, molecules collide, and thermal energy moves through matter long before conscious awareness enters the picture. If many worlds is correct, branch-like structure emerges continually from these ordinary interactions. A deliberate choice is a high-level event built from countless physical processes, not one clean microscopic split. The interpretation is simple in its equations because it adds no special collapse mechanism, yet extravagant in treating separated outcomes as physically real. Some physicists consider that a natural reading of the equations. Others believe it creates difficult questions about probability, identity, and what should count as an existing world. The Born rule remains essential because branch weights still shape what observers should expect before a measurement. How those probabilities should be understood within many worlds remains debated. Experiments have confirmed quantum mechanics with remarkable precision and demonstrated decoherence as a real physical process. Those successes do not uniquely select many worlds over every rival interpretation. Several interpretations reproduce the same ordinary predictions while describing the underlying meaning differently. Many worlds is therefore scientifically serious without being scientifically settled. It offers one coherent answer to the measurement problem, but coherence is not the same as exclusive confirmation. From inside any branch, the limitation is complete. An observer receives one record, remembers one outcome, and continues through one apparent history. The other alternatives remain inside the theory's wider description, yet they never return with a message proving they were there. Two physically identical people begin receiving different information. One hears a door close behind them, while the other remains in silence. One looks toward a window, while the other notices a light changing across the wall. Until that instant, every measurable detail in their bodies and brains may have matched. After it, the agreement begins to weaken. New sensory signals alter neural activity, thoughts develop in different directions, and two lives that once appeared identical start forming separate histories. The physical distinction is easy to describe. The deeper question is harder. Before the divergence, were they one person expressed twice? Or were they always two individuals who merely shared the same qualities? Physics can compare bodies, brain states, locations, and causal histories. It can determine whether two structures match and whether one developed from another. It does not provide a universally accepted rule for deciding when two conscious lives count as one continuing person. Memory seems to offer an answer because it connects the present self to the past. You remember waking earlier, speaking with familiar people, and carrying unfinished thoughts into this moment. That continuity feels private and unique. A perfect counterpart, however, would hold the same remembered evidence. They would recall the same morning, the same conversations, and the same thoughts with equal confidence. Both would say that the past belonged to them. Neither memory would contain a mark identifying one as the original. This does not make memory false. It shows that psychological evidence can be duplicated if the physical structure carrying it is duplicated. Philosopher Derek Parfit argued that personal survival may depend less on an indivisible identity and more on psychological continuity. What matters, in this view, is the preservation of memories, intentions, character, and connected mental life. A separate hidden object, called the self, may not be required to explain why a later person continues an earlier life. This idea becomes difficult when continuity produces more than one successor. Consider a teleporter that records the complete physical structure of a person, destroys the original body, and reconstructs an exact body elsewhere. The reconstructed person wakes with every memory intact. They remember entering the machine and expect others to accept that the transport succeeded. If the original body is gone, many people may be willing to call the result survival. Now change one detail. Suppose the original body remains alive while the reconstruction also wakes. Both people remember entering the device. Both claim the same family, promises, possessions, and private past. They cannot both occupy one location, and they cannot continue as one stream of experience. The thought experiment reveals that perfect reconstruction and personal identity are not automatically the same claim. Imagine waking after the process. Your eyes open in a familiar room. Your memories feel continuous rather than newly installed. Nothing inside experience announces that another person with the same past exists elsewhere. You remain confined to one point of view, one field of sensation, and one sequence of thoughts. The other person awakens with the same certainty, yet no awareness passes between you. From outside, the structures may be indistinguishable. From inside, each consciousness remains private. The ship of Theseus raises a related problem through gradual replacement. A wooden ship can have one damaged plank replaced, then another, until none of the original material remains. People often continue to call it the same ship because the change happened through an unbroken history. Human bodies undergo their own gradual changes. Cells die, material is replaced, memories shift, and personality develops across time. Personal identity already survives considerable physical transformation in ordinary life. This suggests that exact material sameness cannot be the only thing that matters. Continuity, causation, and the way later states grow from earlier ones also appear important. A duplicate complicates this because two later lives may connect equally well to one earlier pattern. The relationship branches where ordinary identity usually continues along one line. Physicalism makes such duplication conceptually possible if mental life depends on physical organization. It does not settle whether matching organization produces the same subject or two subjects with identical contents. Consciousness itself remains incompletely understood. Neuroscience can connect experiences to brain activity, but it has not explained why physical processing feels like anything from the first-person perspective. The existence of matching neural states would therefore answer one scientific question while leaving another untouched. An observer could describe every cell, connection, and electrical signal in both brains. That description might preserve everything visible from outside. It would still not reveal whether one point of view had somehow become two, or whether two points of view had existed from the moment duplication occurred. The difference between qualitative identity and numerical identity matters here. Two people can be identical in qualities while remaining two separate individuals. The same design does not create one shared location, one shared causal history, or one shared awareness. As soon as experience differs, their personalities and memories begin developing apart. Over time, even the resemblance that made the problem possible would gradually fade. The most careful conclusion is therefore limited. A perfect physical copy could preserve every describable feature of a person at one moment. It could preserve memory, dispositions, expectation, and outward behavior. Whether it preserves the same conscious subject is not something current physics can decide. Duplication may reproduce everything that can be observed from the outside, while leaving the private fact of being someone unresolved. A person decides whether to make a difficult phone call. The choice is small enough to seem ordinary, yet its effects may continue through trust, work, health, or a relationship. One response can ease a conflict, another can allow silence to deepen. Neither outcome requires a dramatic quantum event that cleanly divides a life into two complete stories. Human decisions emerge from enormous networks of physical activity. Memories, emotions, habits, sensory information, and imagined consequences all influence the brain before an action occurs. Countless microscopic interactions contribute to that process, but no single particle usually represents the entire choice. This is why the statement that every possible decision creates a separate universe is too simple. Many worlds does not imply that every story a person can invent becomes physically real. The quantum state supports only outcomes permitted by physical law and by the conditions that actually exist. A person cannot create a branch where gravity stops working merely by wishing for it. An imagined future is not automatically a physically supported alternative. Even when different outcomes appear in separate branches, the decision-making process remains part of the causal chain within each one. Reasons influence attention. Attention changes behavior. Behavior alters the conditions that follow. The existence of another possible result does not remove those connections. Within each history, actions still leave effects that later events must inherit. The Born rule adds another important limit. It assigns different relative probabilities to possible quantum results. The presence of several branches does not mean that every branch should be treated as equally expected. Physicists do not simply count complete universes as though each outcome were one identical ticket in a box. Branch weight describes how strongly an outcome contributes to rational expectation before the result is known. The exact meaning of probability within many worlds remains debated. Some researchers argue that the Born rule can be recovered from rational decision-making or from the structure of the quantum state. Others believe the interpretation has not fully explained why those weights should guide expectation in the familiar way. The disagreement is technical, but its practical lesson is clear. A very low-weight outcome existing somewhere would not make reckless behavior sensible. Here, weather forecasts offer a simpler comparison. A forecast can contain several possible conditions with different levels of support. The fact that clear skies remain possible does not justify ignoring a strong warning of dangerous wind. Rational action depends on the weighted possibilities relevant to the observer, not on the bare existence of every allowed outcome. The same logic applies to quantum branches. A person should not behave as though another history will absorb the cost of a harmful decision. No other branch absorbs this branch's consequences. Compatibilist accounts of free will approach the problem from another direction. They do not require a person to stand outside physics. Instead, they ask whether an action follows from the individual's own reasoning, intentions, values, and understanding, rather than from external coercion. Under this view, freedom is not the absence of causes. It is the ability of a person's internal reasons to become part of what causes the action. A decision can therefore remain meaningful even if every thought has a physical basis. The reasoning matters because changing the reasons can change what happens. Warnings, education, reflection, and experience all influence future behavior through ordinary cause and effect. Many worlds does not erase that process. It places possible outcomes inside a larger physical description, while leaving each observer inside one unfolding record. Consider the earlier phone call. Again, one choice may open a conversation that changes the following week. Words spoken during that call may affect another person's sleep, confidence, or willingness to respond. That person may then act differently towards someone else. The effect continues outward through ordinary days without announcing itself as a major turning point. A second possible history cannot carry those words back into this one. It cannot repair the silence here or receive the apology that was never given. Regret, therefore, remains local. Another distant counterpart or quantum outcome cannot live this history on your behalf. It cannot return lost time, remove damage, or transfer wisdom between separated lives. The possibility that events unfold differently elsewhere may change the map of existence. It does not change the road beneath the traveler standing here. Other roads may exist, but each one still leads its own traveler toward a local destination. In this history, causes continue to produce effects, and choices remain among those causes. Place the major claims on an imaginary table, arranged not by how dramatic they sound, but by how firmly they are supported. At one end lie direct observations. At the other lie interpretations and extrapolations that may be coherent without being confirmed. The distinction matters because the word multiverse often compresses all these levels into one idea that can make a measured feature of the cosmos sound equivalent to an inaccessible duplicate, even though the evidence behind them is very different. The strongest ground begins with what instruments repeatedly detect. The universe is expanding. Ancient background radiation fills the sky. Large-scale measurements are consistent with space being close to flat within current limits. Quantum experiments produce interference and probability patterns with exceptional reliability. Decoherence can be observed as interactions spread quantum information into the surrounding environment. These are physical results, not philosophical preferences. The next level contains motivated inference. Researchers observe broad uniformity across the visible cosmos and extend that pattern beyond the horizon. They consider models in which space continues farther than we can see, and ask whether known laws remain valid in causally disconnected regions. Each step has a reason, yet none becomes a direct view of what lies beyond observation. The total size and global topology of the universe remain unresolved. An unfinished map can contain blank areas, but the empty paper does not permit every possible coastline. Farther along the table sit model-dependent consequences. Eternal inflation appears naturally in many inflationary models, but pocket regions have not been directly observed. Cosmic recurrence follows only if space extends without limit. Local states are suitably restricted. Matter continues with similar statistical behavior, and the same laws remain in force. Many worlds preserves the continuous evolution of the wave function, yet rival interpretations can reproduce the same ordinary experimental predictions. A possible universe is not an observed universe. Science can accept unseen entities when a broader theory predicts measurable consequences with unusual success. The difficulty grows when a proposal places its most distinctive consequences forever outside causal contact. If no signal can reach us from another inflationary region, direct confirmation may be impossible. If a perfect cosmic counterpart lies beyond every observable horizon, no telescope can locate it. If rival quantum interpretations make identical predictions for every accessible experiment, evidence may not select between them. This is the core of the testability objection. A scientific proposal gains strength when observations could have turned out differently and therefore could have counted against it. A claim protected from every possible result risks becoming impossible to separate from an unsupported story. Defenders answer that inaccessible entities can still belong to science when they arise from theories tested elsewhere. If inflation explains measured cosmic features and eternal behavior follows from the correct model, unseen regions may be consequences rather than inventions. If the quantum formalism remains universal and collapse is unnecessary, branching histories may belong to what the mathematics describes. The debate concerns how much evidential weight those indirect roots should carry. It also concerns parsimony, the preference for explanations that account for more while adding fewer independent assumptions. One interpretation may use simpler equations while asking us to accept a much larger picture of existence. Another may describe one experienced outcome while adding a collapse rule absent from the underlying dynamics. The measure problem adds another layer of uncertainty. In an infinite collection, every allowed type of event may occur endlessly. If both common and rare outcomes happen without limit, ordinary counting stops giving useful probabilities. A similar challenge appears in branching descriptions when physicists ask how relative weights should guide expectation. Comparison becomes difficult when the total collection has no finite count. Now picture a telescope pointed into the oldest light it can ever receive. Its detectors gather faint radiation that has crossed nearly the entire observable history of the cosmos. Beyond that signal lies no visible wall. There is only a limit on what information can arrive. The instrument waits without receiving a message from farther away. Its silence cannot prove that nothing exists there. It also cannot confirm whichever theory feels most compelling. That boundary is where disciplined curiosity must replace certainty. The honest conclusion is conditional. Observation supports the measured universe. Inference extends its patterns. Interpretation asks what the equations mean, and speculation explores what may follow beyond direct tests. Each level can be valuable, but none should borrow certainty from the one below it. The dramatic answer matters less than the conditions required to reach it. The dark window still returns a single reflection. The room behind it remains familiar, while the space beyond the glass reveals almost nothing. Earlier, that one visible face may have seemed like evidence of uniqueness. Now it carries a narrower meaning. It confirms one local point of view, one body receiving information from one place, and one mind continuing through one accessible history. It says nothing certain about how many similar arrangements might exist beyond the reach of observation. Perhaps another person with the same memories stands beneath a distant sky. Perhaps quantum theory contains separated histories in which another outcome was recorded. Perhaps the universe is finite, and no complete counterpart has ever existed. None of these possibilities changes which life is available from here. A perfect duplicate would not remember on your behalf. They could not receive the consequences of a promise you made, repair a relationship you damaged, or carry the comfort meant for someone beside you. Their thoughts would remain inside another chain of physical causes. No memory, responsibility, or relief could cross the separation. That makes causal connection more important than simple resemblance. Many stars exist, yet none can replace the sun for Earth. Their light may be equally real, and some may be similar in size or temperature, but this planet depends on one nearby star through a specific physical history. Meaning can work in a similar way without becoming a law of physics. A person may resemble another person closely, yet one particular relationship cannot be exchanged for a distant match. The shared conversations, injuries, forgiveness, and time spent together belong to a connected history. Even an exact copy elsewhere would not stand inside those connections. Abundance is not the same as replaceability. A book can be printed many times while one particular copy still carries handwritten notes from a parent, a friend, or someone who is no longer alive. The printed words may match every other edition. The marks inside that copy belong to one sequence of contact, memory, and care. In the same way, the possible existence of matching lives would not remove the local history through which this one acquired its consequences. Physics does not instruct anyone how to feel about that possibility. Some people may find the idea isolating because every counterpart would remain unreachable. Others may find it quietly comforting because existence could contain more possibility than one visible history reveals. Neither response follows directly from an equation. A cosmological model can describe the possible extent of space. A quantum interpretation can describe how alternatives remain within a mathematical framework. Neither can assign personal value to a morning, a conversation, or the presence of another person. Scientific structure and personal meaning answer different kinds of questions. Confusing them can turn a physical proposal into a spiritual claim it was never designed to support. The careful position leaves both possibilities open. There may be matching instances scattered through an enormous cosmos, or this arrangement may occur only once. The lived importance of this moment does not depend on resolving that question. It depends on the fact that causes connect this moment to what comes after it. A word spoken here can be heard by someone nearby. A decision made here can alter tomorrow. A kindness offered here enters a history that no inaccessible counterpart can enter for you. Outside the window, the night remains silent. The reflection moves slightly as you breathe. The glass holds one visible room against a darkness that may conceal more space than any observer could ever know. Nothing beyond it confirms another Earth, another branch, or another person carrying the same past. Nothing beyond it proves that you are the only one. The room does not need to answer that question. This consciousness still opens onto one perspective. This body still occupies one place. This life may not be cosmically unique, but it remains the only one that can be lived from inside here.